Let's look now at an application of dynamic memory allocation. So what we're looking at here is a slightly modified version of a homework assignment I gave in an intermediate programming class in C. So here's the requirements that the students were given. First, don't use structures. That would make it too easy to do some of the things that I wanted the students to do here. And of course, the purpose of the assignment is to learn something new. We weren't going to hard code any file names of data in our program, so instead we would use redirection by reading from standard in to get the file contents. So my program will never know this actual file name, it just gets the contents of the file. The dynamic memory allocation part comes in at lines 3 and 4 here, or sections 3 and 4. So what I want them to do is read the data and store the file contents in a dynamically allocated array of strings. And in each case, each line needs to be just long enough to store that particular line. One of the advantages of what are essentially two-dimensional arrays that are dynamically allocated is that they don't have to all be the same length anymore, unlike if you create an array, a two-dimensional array in the traditional sense. Initially, they'll start off by allocating enough memory to store 5 addresses, which would be tied to potentially 5 lines of the file. But if that's not big enough, and I made the assignment such that in many cases it wouldn't be, then they need to reallocate the space, doubling how many addresses they can store. So basically they need to grow the number of lines of the file that they can store in their program. We know that the first line of the file will be what's called a header line that describes each column. And we're going to look at some data here in a moment, so all this will make more sense then. One of the problems though with the data is that the columns that we're interested in aren't always in the same position. Meaning we're going to look, if we look down here, we're looking for the columns that have titles of name and item. But in some files, name could be in the first column, another file may be in the third column, whatever. We do know that name will always come before item, but beyond that, we don't know which particular columns they'll be in. So eventually what we need to do is determine which columns contain the name and the item, and then for the lines after the header file, print the contents of those particular columns. So print the person's name and the item that's on that line. I didn't want the students to create other arrays to store these things individually. Instead, I want you to store the lines from the file, and then later when it's time to print, simply extract the information that you want. And then I told them that this is what we know that we can then essentially hard code into our program. You always have to know something, but we would like to minimize a lot of the hard coding so our program can be used in a more general way. So I told them that we knew each line would consist of comma delimited tokens. The first line would be the header line. The number of tokens per line can vary. The line can be stored 150 bytes. The columns that we wish to print have column headings of name and item, and name is always to the left of item. Nothing else should have been hard coded in the particular program that's tied to that particular data. And I gave them a data generation program that would produce 10 data files with things in different places to try to force them to quit hard coding. As far as output's concerned, every time they reallocate, they need to print a message indicating that's what they're doing, which not only helped them in debugging, but helped me see that they really were doing the reallocation. And then finally print the name and item combinations from the lines. All right, so let's look at some data and see what we're dealing with here. So here's the first data file. So you can notice most of this is garbage, but there's name, which is in the second column. So that means in the second column of every line below this, there's a person's name. Christopher, Vipul, Marco, Vipul again, David, and so forth. There's garbage, there's some garbage. Now in the fifth line is item. So in the fifth line of here, we have shoes, flowers, shoes, phone, and so forth. Let's look at a different line, or a different file, excuse me. So now name is in the third column. Item is still in the fifth column. I think that's what it was before. Let's try another one. Name is third, item is fifth. Hopefully I'm not seeing a pattern here. There's name is first, and item now is third, with a bunch of other garbage and so forth. So you can see things do vary. So let's look at the program, and we'll see that I've written pseudocode in several different places as well. So at the top I have what I call my big picture pseudocode. That's pseudocode representing the overall process. So based upon what I just saw and looking at the data, I know I need to read a file from standard in. Initially I will allocate memory to store 5 lines. Then once I've stored, or done this, for each line of the file, if there's not enough memory to store the additional line that I'm currently reading, then I will reallocate to double the potential lines. Otherwise, I store that current line. And then after I've stored all the lines, then for each string in the array, tokenize the line, printing the appropriate column values. So what does the output even look like? Let's look at this. So I'm compiling this program that we're currently looking at. And since I'm reading from standard in, I use the less than here to redirect one of the data files. And in this case, you can see it reallocated twice, doubling the space because it started at 5 the first time. Here's the column headings, and here's that stuff we were looking at. So if we look at that file again, we can see this line there: Christopher shoes, Vipul flowers, Marco shoes, and so forth. So I'm getting that stuff. The last line, Arandi shoes, there's Arandi and shoes. And one reason for reading from standard in is so I can do something like this. So I had 10 data files. So let's clear this out. So on Linux-like or Unix-like systems, which includes Linux or Mac OS, I'm using what's called the bash shell. So we can see what my shell is. It says it's bash. So it has its own programming language. So I'm going to say for F, and that's just the variable name I'm going to use, for F in, and I want the things that match that pattern I just showed you. So those would be din, short for dynamic-data01.csv, din-data02.csv, and so forth. I'm going to do this. I'm going to run my program. In fact, let's put some headers in here to separate some stuff, or we'll do that after a moment. So I'm running my program, redirecting in the file that matches what we just found. We'll put a blank line here, or a couple blank lines. Oops, I just screwed that up. So it should have been done. So let's fix that. And it doesn't like my new lines. What's the problem with that? Let's do this. This will work. All right. So now I just went through all 10 files. So for the first one, there's the reallocation messages. There's the contents. The next one, the messages, the contents. This one I had to reallocate once because it was a short file, the contents, and so forth. Don't number that long. But you can see what's happening here. So we talked about the big picture pseudocode. Let's see how that translates into stuff. So we said that we know that name and item are the labels, but eventually I have to figure out what columns they correspond to. And this is going to be the pointer to my strings. So let's look at an example and see briefly what I mean by that. So let's say that our data looks like this. Some garbage, comma, name, garbage, comma, item, garbage. And then we have garbage, Ralph, garbage, phone, garbage, Susie, garbage, shoes, is one of the possible items, and so forth. So I want to store each of these. So initially I'm going to store, this is an array of characters, right? So we can think of it as being this. So it'll be a null terminated array of characters when I read it in, because I'm going to use fgetString as a function to read it in. So it's going to store it in a buffer, and I'm just going to save it. So we'll have something like this. Line 1. These are dynamically allocated. So these really actually also could be longer. That's one of the benefits of dynamic memory allocation is these don't have to be the same length. So I'll look at the particular line and figure out how many characters I need. So maybe this is line 2. Maybe this is line 3. We'll just do 3 of these instead of 5. Well, when I use malloc for these, they return something of char star, or what I'm going to treat as char star is actually what it is. So return that address. I want to store these, and this is the part that I need to grow as necessary. So if I only had 3 originally and there was 4 lines in the file, when I get to the 4th line, then I need to double this down to 6. Well, this is an array of char stars, which means I need something of type char star star to store the address for this block. So these don't grow. These are just the size they need to be, which is what? I need to be careful here because remember I need enough room to store the terminating nulls. And then also depending on what I choose to do, since these are lines in a file, they also will have new lines at the end. I can strip those out, but if I store those, I need to have enough memory for those. But that will be taken care of along the way. But this is the part that needs to grow each time with the address remaining in lines. All right, so back to this. So I'm going to have a line counter. I don't ultimately know how many lines there will be in the file. Number of labels. I could have just put 2, but if I want to add more labels, I could do that. And this right here will change to be whatever the number of labels is. And then here's lines. So see it's of type char star star. That will store my dynamically allocated array of strings. So read file will get the address of the lines count variable so it can update it via a pointer, and then it's going to return the address that I assigned to lines. And then once we have all that stuff, then I can print the appropriate columns, and then I need to free the memory. So read file is the important part. Let's look at that. So it has its own pseudocode because saying that I need to read a file is certainly important at the big picture, but now I need to understand more of the problem. So here's my pseudocode. For each line of the file, if there are enough character pointers, that is, if I can store another string, then allocate memory for that line and store the line. Otherwise, double the number of character pointers, allocate memory for the line and store the line. And then somewhere here, what I really should have probably said was increment line count. Something like that. So here's my buffer. I knew that a line could fit within 150 bytes total. Here's where I'm going to put that the initial size is 5. And I stored this as a variable because I'm going to use this later to keep track of things. Here's where I'm allocating enough space to store the addresses for 5 lines, like I showed you in the example. And now I'm going to start looping through the lines using fgetString. So first I check to make sure I can even store a line. So let's see how that works. So let's say I have this. So I have line 1. So this is in the file. And we have line 2. Let's say we have line 3. And we'll say, keep this short, that max lines equals 2. And then I also have a line counter. So line count equals 0 to start with. So initially I allocate memory to store 2 lines of the file. So I'm going to check once to see, are these the same? They're not. So I know I have memory here. So I'm going to allocate memory to store line 1. And I do store line 1. Loop back up. This is now 1. I'm ready to store line 2. These aren't the same. So I'm ready to store line 2. Allocate memory for that. Line 2. Increment my counter to 2. Loop back up. I now want to store line 3. But now max lines and line count are the same, 2. So I know there's not enough memory. So this is where I'm going to double this. Maybe I should have done like that. Change max lines now to 4. Right? And now continue with the other part, which is store line 3. And change this to 3. That's the logic here. Depending on how you choose to do it, whether you say line count is already incremented to 1 or whatever you might use, while line count is less than max lines, keep going or whatever. It's an implementation decision. So here's where I say if star lines count, remember, I passed in the address of the lines count variable because I cannot return 2 things. So I chose to return the address of the array of strings, so I'm going to use a pointer here to get the lines count back at the calling location. So star lines count refers back to the original place in memory. So if they're equal, here's where I'm going to double max lines. I call realloc. I give it the name of the dynamically allocated array that we're currently using. And then here's where I tell it the size that I need it to be, which is max lines. That's why I went ahead and did it here. Max lines times the size of the objects that I'm storing. If realloc meets my request, it will give me back the address of the memory that I can use. But if it can't meet my request, then it's going to return null. So I check here to see if it can do that. Otherwise, if it returns null, I'm going to say there's a problem and exit. Otherwise, I'm going to print my reallocation message and move on. And then, since I called this temp, I'm going to reassign temp to lines. One of the things you have to be careful of here, it's not a problem in this program, but if I was trying to return the lines pointer as a pointer itself back to the calling location, I have to be careful because when we use realloc can do one of 3 things. So let's say here's my initial space. If realloc needs to grow this space and this spot in memory is free, then it may simply extend it and return the same address that it was initially given. That's one option. Second option. Here's the initial memory, but this space is being used or somewhere over here, so I can't grow it. So what realloc may do instead, it says, well, over here is something big enough to do what you want, so I'm going to return this address, which is different than the address that was given. And the third thing is, I simply can't do what you want, so I return null. In the code I have, my program can deal with either of these situations without any problems. But if you're trying to reallocate the space, assuming you know the initial address and it uses this instead, and you don't somehow get this new address back to the calling location, you can have problems. But for the way I implemented it, that it's never even an issue. But I have seen people get burned by that, including me, under other circumstances. All right? So at this point, we've either grown our space and then we want to store the lines, or we don't need to grow the space and then we store the lines. So where do we store? Well, I have a line counter, which also serves as my index into where to store things. Remember that star lines count was initialized to 0. So initially, I want to store the first line of the file in lines 0. That's at the 0 index of the array of strings. And the size is string length of buffer, which stores the line from the file, plus 1 times size of a char. Now, size of a char is 1, but I do this more as a reminder of how to think about the problem. I could leave this part out and it still would work. Why did I add 1 here? Well, string length will give you the number of characters in the string excluding the terminating null. So I need to also have room for the terminating null, so I need to add the 1. Now that I've done this, Now I can copy, all this does is allocate memory. Now I can take the line from the file, which is currently stored in buffer, because that's where fgetString stored it, take the current line of the file and store it into my array of strings in this dynamically allocated memory. Just like what I showed you here. As I read the lines, I would allocate memory first, then copy line into the memory. Allocate memory, copy a line into the memory, and so forth. Then I update my line counter and keep going. And since I was printing reallocation messages along the way, then I throw a new line in here. And then finally I'm going to return the address to the array of strings. All right? So let's go back to the calling location and see what's happening. So now we're going to print the columns. But that was in their entirety. So that included all the garbage. I need to find the appropriate columns and then just print the person's name and the item associated with that person. Maybe they bought something. All right, so let's look at print columns. So this has its own pseudocode. So let's look at that. So allocate memory to store the indices of the labels. I don't know how many labels there are. Actually, that's passed in. Sorry, so I do know that here. But I don't have anything to store what locations they're in. Are they in the first column, the 8th column, the 4th column, whatever? I'm going to allocate memory to store those. So I did that here, and I chose to initialize it to 0, but I don't think I really need that. But by using calloc, it does get initialized to 0. So now I'm going to store the string that I was just passed in. Why do that? Because the string toke function modifies the existing string by replacing the delimiters with a terminating null. So if I wanted to reuse one of the strings that I stored, which I'm going to do here in a minute, then I would have a problem. So instead, I copy that line to a new buffer, and then I tokenize that new buffer. So first of all, I need to find the columns, and I will pass in this array that can store the 2 indices in this case, as well as the labels I'm looking for and the number labels. So let's look at find columns. It has its own pseudocode. So for each token in a line, for each label, if the token is equal to that label, then store the label index. So what that means is I extract a token from a line and then I say, is this the name label? Is this the item label? If it's either one of those, then I'm going to store the current column count. And I guess you really could swap those. I could have started with each label, go through the tokens. But the problem with doing that is I would have to basically start fresh each time, and then I'd have to make another copy of the string because of the fact it would modify it on the fly. So by the time I get to the bottom of this function, I should know which columns contain the name label and the item label. I haven't extracted the people's names and the items themselves. This is just to figure out which columns to work with. So now that I know that, let's go back to our pseudocode. Allocate memory to store the indices. For each label, find the index of the label. That's what we just described. And now for each label index, get the token at that column index and print the token. So for example, if I know my indices, so like I have here, so this is index, this is column 1, this is column 2, so we need that, 3, 4, this is column 5, then I need to go through here and on this line right here, print column 2, which is Ralph, and print column 5, which is phone. Then on this line, print column 2, which is Susie, print column 5, which is shoes. So I found the columns. I had made a copy of the line. So now I can actually mess up the line. It doesn't matter necessarily. But here I'm making a copy again. So I'm going to start tokenizing. And then I'm keeping track of the token count so I can match it up with which columns I'm in. And when I get to the appropriate point, then I'm going to print that token. So I print the person's name first. And I notice we have a comma here. in the output. I do this right here, so I add a comma after the person's name, but not a comma after the item. So I'm just anal about that, but this allows me to know to print commas after all the preceding things. And once again, I'm thinking ahead to where I could have more than two columns that I'm interested in and dealing with it. So I just keep going through, found Austin in this case, comma, found shoes, printed it, and so forth. So let's go back and see. I think we've done everything. So that was doing the printing. All that's left is free mem. So I give it the lines here, which is my array of strings, lines count. Here's my function for doing that. I free each of the individual lines themselves. Then I free the block of memory that stores the addresses for the lines. And then my program's done. So this program actually covered a lot of things that I've discussed in previous videos. Reading from standard in instead of a hard-coded file name. We created an array of strings, which I talked about in another video that dealt with dynamic memory allocation examples. We had to be smart about things. We did a lot of tokenization. I'm thinking about scalability because I'm thinking about the fact that I can put these names and items in different columns and my program still works. We dealt with dynamic memory allocation, which was the underlying purposes of assignment. There's all kinds of things finally coming together here. And so if you've been watching the other videos, hopefully you're starting to see the bigger picture about how I use all those language components that we've discussed. So that's the example for dynamic memory allocation.